Okay, today we are going to talk about electric potential and parallel plates. We want to be able to analyze the motion of charged particles in order to determine their electric potential. So there's a little bit of background that we need first. So this works very similarly to the force against gravity. When we did work against the force due to gravity, we created a gravitational potential. We gave the object a gravitational potential energy. And the same procedure applies for electric fields. If you move a charge against an electric field, you must apply a force for some distance. Therefore, you're doing work and you give it electrical potential energy. The work done in order to move that charged object is called the electric potential difference, or V. Okay, so the unit of electric potential is a volt, and the volt is equal to 1 joule per coulomb. Okay, if you did 1 joule of work in moving a charge of 1 coulomb in an electric field, the electric potential difference between those points would be 1 volt. This is in your reference table. This is the equation we're talking about, where V is in volts, W is work in joules, and Q is your charge in coulombs. So here's an example. It says a potential difference of 10 volts exists between 2 points, A and B, within an electric field. What is the magnitude of charge that requires 2 times 10 to the second joules of work to move it from A to B? So we know that V is equal to 10 volts, and the work is equal to 2 times 10 to the minus 2 joules. So we just plug this in, and we're looking for Q, the charge, so it's V equals W over Q, and we just solve for Q, so it's 2 times 10 to the negative second joules divided by 10 volts is equal to 2 times 10 to the negative third coulombs. So then we can talk about the electron volt. Physicists created an alternate unit for electrical energy and work that can be a little bit more convenient than joules, because if you noticed here, this is times 10 to the negative 3 coulombs, and that's kind of small. So, so maybe we want to use an electron volt. So, an electron volt is the amount of work done in moving an elementary charge through a potential difference of 1 volt. And 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. This is in your reference table. Oops. That's in the reference table. Okay, so here's an example. So this is an EV example. It says a proton is moved through a potential difference of 10 volts in an electric field. How much work in electron volts was required to move this proton? So we say 10 volts. This is V is equal to 10 volts. And then we're looking for work. And this is a proton, so Q is equal to 1 elementary charge. So we can say that the work is equal to QV, just like here. And so then we can plug this in. 1 elementary charge times 10 volts is equal to 10 EV. And then you're done. That's all you have to do to answer that in terms of electron volts. So now we're going to talk about the Millikan oil drop experiment. This was something that was done by Millikan, and what he did was he found the charge on an electron. And he knew that what the voltage was that he needed to suspend oil drops. So what he had was 2 parallel plates, and they were suspended so that the force due to gravity was down, and there was an electric force that made it so that the oil drops didn't move, and they were suspended right there. So he knew the voltage needed to suspend the oil drop, and he built the machine so he knew the distance between the plates. and he knew gravity. So all that was left was the mass of the oil drops, which changed for each drop. And he figured it out with some interesting math that we don't have to cover right now. But he found out that each of these oil drops had a common value of 1.6 times 10 to the negative 19th coulombs for a single electron, and that's where that charge comes from. So what happens is we have the voltage, we know the voltage here, and it's equal to work divided by Q. So that means that work is equal to voltage times Q, the potential difference times Q, and work is also equal to force times distance. Therefore, force times distance is equal to potential difference times Q. And if we rearrange this, it's the electric force divided by the charge is equal to the potential difference divided by distance. So then to solve for Q, Q is equal to force times distance divided by voltage. This equation, not in the reference table. You do need to know this. This is something you need to know. Since the electric force and the gravitational force, the equation then becomes Q is equal to mg times d divided by the potential difference.